You know, we usually think of numbers as just, well, numbers, things that count stuff. But what if a number could be more? What if it could actually describe movement, a rotation, or even an entire shape in two dimensions? Today, we're going to dive into the visual world of so-called imaginary numbers. And I promise you, you'll see they're anything but imaginary.
So let's just start with a puzzle. We're all used to using two numbers, right? An x and a y coordinate, to pin down a point on a map. But how could you possibly do that with just one single number? That's the core question we're going to tackle.
To figure that out, we have to go back to basics. We're starting with something we all know, the good old number line. But as you're about to see, its greatest strength is also its biggest weakness.
Look, the number line is great for moving back and forth. You want to go right? Use a positive number. Want to go left? Use a negative one. Super simple. But that's it. That's all it's got. It's a one-way street, or I guess a two-way street on a single line. To break out of that line, we need to completely rethink how we see math.
Okay, so here's the big mental leap we need to make. We're taught that multiplication is just scaling, making a number bigger or smaller. But what if we thought about it as a physical action? What if multiplying a number could also mean rotating it?
This one idea is the key that unlocks absolutely everything. Just think about it for a second. If you have a positive number, say 3, and you multiply it by -1, you get -3. You've just flipped it to the other side of 0 on the number line.
Let's actually picture this. Imagine the number 1 isn't just a dot on the line. Imagine it's an arrow, a vector, that starts at 0 and points right at 1. It's got a length and it's got a direction.
So when we multiply that arrow by -1, we end up pointing at -1. Geometrically, what did we just do? We rotated that arrow 180 degrees around the center. It's the exact same thing. Multiplying by -1 is a 180-degree rotation. And that leads to a really fascinating question. If there's a number for a 180-degree turn, are there numbers for other kinds of turns? This is where the magic really starts. It's the next logical step, right? A full 180-degree turn is one multiplication by -1. What if we wanted to get there in two smaller equal steps? What number, when you multiply by it twice, gets you that 180-degree rotation? Or to put it another way, what number times itself equals -1?
And the answer is the imaginary unit I. That's its whole job. By definition, I squared is -1. So if multiplying by -1 is a 180-degree turn and doing two I multiplications gets you there, then a single multiplication by I must be half that journey. It must be a 90-degree rotation. So let's do it. We take our arrow pointing to 1, we multiply by I, and bam! It rotates 90 degrees. But wait, where's it pointing now? It can't be on the old number line. It's pointing straight up into a whole new dimension. And just like that, we've created the imaginary axis. And there it is. We've broken free. We're not stuck on a line anymore. We have a whole two-dimensional surface, the complex plane. And now, any point on this plane, what we used to call x, y, can be described with one single number. It's like a set of directions. Go x distance along the real axis and iy distance along the imaginary axis. Okay, so now that we've built this new playground, let's see how the old rules of math play out. It turns out that basic arithmetic now has these beautiful, really intuitive geometric meanings. It's like a new language for movement. So, adding two complex numbers is surprisingly simple. Think of it like a journey. You travel along the path of the first number, z. Then, from where you stopped, you travel along the path of the second number, w. The spot where you end up, that's c plus w. It's just adding two trips together. Subtraction is also incredibly cool. The number z minus w isn't just some abstract answer. It's the actual vector, the direct path that takes you from the point w to the point z. It perfectly describes the relationship and the distance between them. And multiplication? Oh, it gets a massive upgrade. Back on the number line, multiplication just stretched or squished your vector. But in the complex plane, it does two things at once. It scales the vector's length, and it rotates it. It's a stretch and a spin combined into one elegant move. So, what's the point of all this? Where's the big payoff? Well, this is where it gets really beautiful. We can now use this new language to describe geometric shapes with an elegance that's just stunning. Remember the old equation for a circle from high school? X squared plus y squared equals r squared, all that stuff. Well, in the complex plane, it's just this. This equation literally says, in plain English,
The distance between any point z on the circle and the center point A is always equal to the radius, r.
And that's what makes it so powerful. It's not a formula you have to memorize, it's just a description of what a circle is. It's a set of points that are all the same distance from the middle. The math is a direct translation of the idea.
And this incredible simplicity isn't just for circles. It works for all kinds of geometry problems. As this document points out, proving that 4 points make a perfect square, which can be pretty tedious with regular coordinates, becomes way more straightforward when you can use these geometric tools.
I mean, check this out. How would you build a square? It's almost like a recipe. First, you define one side as the vector between 2 points. Step 2, you need the next side, right? Well, just rotate that first vector 90 degrees. How? By multiplying it by I. Then you just add that new side to your starting point, and there's your third corner. It's construction by pure rotation.
So let's just step back for a second and see what we've really done here. We've taken this idea that sounds totally abstract, imaginary, and we've shown that it's actually one of the most natural ways to describe the 2D world around us.
So what's the big takeaway? Complex numbers aren't some weird trick. They are the native language of 2D space. That little letter I isn't just the square root of -1, it's the command for rotate 90 degrees. And when you speak this language, simple math like adding and multiplying become powerful geometric actions, letting us describe complicated shapes with beautiful, simple equations.
And that leaves us with one last, kind of mind-bending question to chew on. We've just seen how we can describe the geometry of a 2D plane with this amazing system. So, what about our world? Is there another, even more amazing language out there that can describe the geometry of the three-dimensional space we live in? Something to think about. Thanks for tuning in.